I also explained a heap can be stored in an array. And in an array, we can access the parent node and the child node in constant time using these formulas. Today, I will explain the height of a node. The height of a node is defined like this. The number of edges on the longest simple downward path from the node to a leaf. Look at this vertex, vertex 10. Then it has two simple paths to leaves, and both of them are the longest ones. And there is only one edge, so its height is 1. And how about the height of this? How many simple downward paths from this node? 박정훈. Okay, how many downward paths are there from the node? There are four downward paths. 3? Okay, the longest paths are 3. I'm asking you just simple downward path to leaves, including shorter ones. Okay, 박근배, how many paths? 5 paths, right? 1, 2, 3, 4, 5. And among them, 3 of them are longest, these 3. And there are 3 edges, so the height of this node is 3. Okay? So the height of a node is defined like this. And then the height of a heap is defined in this way. It's the same as the height of the root. So the height of this heap is the height of this root node. And I told you that the height of, the shape of this heap is a nearly complete binary tree. So this height is just big O of log n, because it is a nearly complete binary tree. And now I'll explain max heapify. Max heapify procedure is like this. We are given a node, and there is a precondition. Its right subtree and left subtree should be max heaps. So there is no violation with the key stored in the subtrees. 14 is bigger than 2, and 14 is bigger than 8, and 7 is bigger than 1. But there can be a violation between the root and their children, like this. So 4 is smaller than 14 and is smaller than 7. So this is the input. And this is very important. Their subtrees should be max heaps. Let me explain why it is important later this class. And from this input, we are going to change this subtree into a max heap. Do you have some idea? Kim-Bum-Jin, do you have any idea to convert this subtree into a max heap? The first thing you should do is compare these three numbers, 4, 14, and 7. Then among them, 14 is the biggest one. Then exchange 14 with 4, like this. Then, because 14 is the biggest, there is no violation between 14 and 7, and 14 and 4. But still, there can be some violation in the subtree rooted at 4. Paemin-hee. Then what should we do more? Okay. Compare these three keys and take the biggest one and exchange it with 4. Okay. Then it's done. This is max heapify. Then the running time of max heapify is like this. Actually, picking the biggest one and exchange takes constant time. And what is important is the number of exchanges. Then it is the height of the input node. So it may float down to the bottom. So the running time is big O of h. H is the height of the node. In the worst case, the height can be the height of the heap. So it is big O of log n. Okay, then using this max heapify, let's build a heap, build a max heap. This is the pseudocode of build max heap. So look at this page and try to understand the meaning for a couple of minutes. This is quite strange, yes? And look at the for loop. It's basically, okay, let me show you this. This is the array, and it's heap tree representation. And the small numbers are indices. So basically, we run max heapify from the bottom to top. That is the meaning of this for loop. From larger indices to smaller indices. So we run max heapify from the bottom to top. But look at this. We don't have to apply max Heapify for these nodes. It has only one. It is a leaf, so we don't have to apply max Heapify to them. So we start from here. And it is calculated by 10 divided by 2. And because it's even, we don't have to take the floor. So it's 5. We start from here. Let me explain why this is computed later. Okay, we start from here. Then what should we do with this subtree? 김종빈.
자식 두 개랑 부모랑 비교해서 자식 중에 큰 놈이 부모보다 크면 걔랑 써.
Yeah, so that's the definition of max Heapify, right? But how about this subtree? What should we do? Subtree rooted at 16. What? Nothing? Yes, nothing. Because 16 is bigger than 7, we don't have to do anything. 어미송. Okay, then the next index is 4. So we apply max Heapify on this subtree. And what is the result of applying max Heapify to this subtree? Okay, 14 is promoted and 2 is demoted. So this is the result. The result is like this. 14 and 2 are exchanged. 손광훈. Okay, then the next subtree is this. What should we do? Okay, 3 and 10 are exchanged. And then this, 권다운. The subtree rooted at 1. 김현준.
14랑 16이랑 봤을 때 16이 더 크니까 1이랑 16이랑.
Okay, 16 and 1 are exchanged. Is that all?
그거하고 이제 1이랑 16이랑 바뀌면 1이랑 그 자식 7이랑 또 비교했을 때.
Yes, we have to compare repeatedly. So 1 and 7 are compared, and the 7 is bigger than 1, so they are exchanged again. So we get this. And finally, so 1, we can say in this way, 1 floats down along this path. Okay? Then we apply max Heapify to this root. Then in what path this element floats down? 문경식. Okay, can you tell me the path it floats down? Okay, first 16. So what's next? 14? 8, yes. This key floats down along this path. So this is the result. The answer is just very near to you. Then done. this is the procedure of max Heapify. And I'll ask you a question about this. We applied max Heapify from bottom to top. Why not we apply the procedure from top to bottom? 박용호? Can you explain why we don't apply the procedure from top to bottom? 이동우.
자식이 구려가지고 길을 어떻게 가야 될지 모를 것 같아요.
이정. Let me show you the first. Okay, this is the original example.
위에서부터 시작하고 인카이 더 길어서 비교해야 될 게 더 많아서
Really? 이종하. 정명수.
그래서 비교 더 큰 거를 찾아서 노트노드에 넣어야 되는데 지금 같은 경우에는 4부터 시작을 하면 둘 다 자기보다 작기 때문에 바꿀 수 없지 않아요.
Yes. 16 cannot come to the root node. Why? Let's get back to the definition, problem definition of max Heapify. Do you remember the precondition of max Heapify? This one. When we apply max Heapify to a node, its right subtree, its left subtree and right subtree should be max heaps. To guarantee that, we have to apply those steps from bottom to top. Then the precondition is satisfied, okay? But if we apply the max Heapify from the top, you cannot sure that these two subtrees are already max heaps. In most cases, they aren't. Look at this. This is not a max heap. And this is not a max heap either. So you can't do that. And let me explain the secret of this number. Okay. Look at this. We don't have to consider leaves. The first vertex, the first node we have to consider is the parent of the last index node. Okay, parent. This is the index of last node, and this formula is the formula to calculate its parent. Then let's consider the running time. A rough calculation relates to big O of n log n time, because each max Heapify runs in big O of log n time, and we apply big O of n max heapifies. So a rough calculation leads to big O of n times log n. But a careful calculation leads you to it is big O of n. I will not explain this in detail, but I'll give you some clue. The clue is in a complete binary tree, the half of the nodes is in height 0. And a quarter of them lies in level 1. So most nodes are in low level nodes. So usually the height of subtree in lower level nodes is 0, 1, 2, so it's very small. So if you consider that in calculating the running time, it becomes big O of n. If you are interested in this in detail, look at this page, look at this material, and consult your textbook. Hence, we can build a max heap in linear time. Now it's time to explain another procedure, another important procedure. Extract max. The procedure extract max is to remove the maximum element from a heap. And it is very simple. In a heap, in a max heap, the maximum element is stored in its root. So we just remove 16 from the root. And it takes constant time. But that's not all. We have this, look at this. This is not a heap. So we have to restore the structure to a heap. That is the procedure of extract max. Then how can we change this into a max heap? 최용준, you did or you didn't do? You didn't. Yeah. 최용준, do you have an idea to change this into a heap? Okay, 14 is moved here, and then so 8 is bigger than 7, it is moved here, and then yes, if 4 is moved here, then it satisfied the max heap property, but the shape is different. So, okay, you did well. You showed what I just wanted. But good. That's why the algorithm doesn't work. So we need another way to solve the problem. The answer is we prune this node and move 1 into the root. Then run max heapify. Then no problem. First, we make the shape, and then run max heapify to make it a heap. Okay, then what is the path it flows down along. 한상현, what is the path along which this one floats down?
First change 1 to 14.
14,
Yes. And change 1 and 8.
8,
And change to 1 and 4.
4. Yes, it floats down this path. Then we get a new heap. And obviously, its running time is big O of log n. Okay, now it's time to explain the heap sort. First, an arbitrary array is given. Then first we run the build max heap procedure on the given array. Then, as I told you, in linear time, a heap is built in the input array. Because we use only exchange, there is no additional storage is required. And from the heap, we perform extract max for n times. Then first we get the maximum element. Then we get the second maximum element. So if we place them in a sequence, it is the result of sorting. Basically, the outline of heap sort is the same as that of the selection sort. Okay? Selection sort is selecting the maximum element, and then the second maximum element, and then the third maximum element. Basically the same. But the difference is this. In selection sort, we first need n operations to find the maximum element. And then n minus 1 operations to get the second maximum. So the summation is theta of n squared. But in this case, with the preprocessing time of big O of n, what is the running time of extract max for the maximum element? 한상현. You did. 강인구. Okay. Log n, yes. Then what is the running time for the next second maximum element? Yes. Okay, then log n minus 2. So n is converted to log n minus 1 is converted to log n minus 1. So, and we have to add all these terms. And it is, okay, a simple formula is, it is log n factorial, and it's smaller than log n to the n. So this is n log n. So it is big O of n log. So by using heaps, we greatly reduces the maximum selection time. Okay, let's and I will explain it again using an example. This is a heap. First, we extract 16, and then 1 is moved to the root, and it traverses down along this path. So we get a new heap like this, and 16 is extracted. And then 14 is extracted. Instead, the key 1 is moved to root, and it floats down along, in this case, 10 and 9. And then 10 is extracted, and this time 2 is moved to the top, and it floats down this, 2, 9, 3. Okay. In a similar way, we can extract every element, and then they are sorted. This is the heap sort. And there is one thing I'd like to talk about it, the space. I told you that heap sort is an in-place sort. What is the definition of in-place sort? Only a constant number of additional memory is required, to be exact. Okay? So, consider the merge sort. It needs another array of n elements for merging. Okay? But insertion sort doesn't require any such large memory. But how about this? In this case, we extract something to store it. So it looks like requiring additional memory. Okay? But it doesn't. Look at this. Look at this tree picture carefully. I used only 1, 2, 3, only 10 circles. And each circle represents each memory element. First, I exchange 16 and 1. And then, from there is a barrier here. So the heap is like this, and this is a part of new sorted memory, a sorted array. Can you see this? And step by step, the barrier is moved inside the array. Originally, this array is a heap. Now, after an iteration, the heap is reduced to like this, and this part is a sorted part. And the next iteration, it moves to here. So only one array is enough to store the heap and the output array too. Okay? So there is a magic. The secret of the magic is that. Okay, the pseudocode is given here. And a simple improvement is this. The for loop runs from the largest index to only index 2. We don't perform max heapify, we don't extract the first element. Because after the n-1 iteration, the shape is like this. The sorted part, and there is a heap. And in here, the smallest element is left. So we don't have to run again. Because this element is smaller than all this element, the whole array is the sorted array. This is a minor improvement. Okay, I explained this. Okay, so I explained heap sort until now. From now on, I'll explain the priority queue. And usually the priority queue is maintained or implemented by heaps. Look at this. I think you've never heard of the priority queue, but I'm sure that you have heard of just queue. 이선민, you did. 이치호, what is a queue? FIFO, yes, first in, first out. But the priority queue is a little bit different. Only the with highest priority is out. So keys have priorities, and the highest priority key comes out. So there are 4 main operations for priority queues are like this. The first one is insertion. We insert a new key X into a priority queue S. And the maximum. To get the maximum value of the priority queue. And extract max. The difference between these two operations is whether you remove the maximum element or not. Extract max removes the maximum element from the queue. And then finally, the priorities of keys can be changed. Usually they are increased. So let me explain them one by one. And assume that we implement those operations using heaps. Then these two operations are quite simple. I already explained the extract max. It's like this. Remove the key in the root and readjust the key to make it a heap. And the operation maximum is very simple. We just read the value stored in the root. So it takes constant time. This is a new operation, increase key. It is like this. This is a heap, and 4 is in level 0. Level 0 and its value is increased to 15. In this case, it traverses up the tree. First, we exchange 8 and 15 because 8 is smaller than 15. Then note that there is no violation between these three keys because 15 is bigger than 8. 2 is still smaller than 15. And then only violation only happens between 15 and its parent. So we repeatedly traverse up the tree until a bigger element appears, like this. So what's the running time? 최경렬. What is the running time? Big O of n log n? Technically it's true because it's smaller than that. But there is a tight bound. Big O of n. Okay, if you do this repeatedly, you can find a tighter bound, but 홍동균, log n, big O of log n, because the height of the tree is big O of log n, so it is big O of log n. And then finally, the insertion operation. Insert a new key in a heap. And it's not difficult. It's the same as like this. I'd like to insert a new key, 10, in this heap. First, I will add a new node and place 10 here. Then, do the same thing as we did after we increase a key. So 10 is bigger than 7, they are swapped. And then, in this case, 10 is smaller than 15, so we don't have to do anything more. It stops. Okay. And so there are 2 programming assignments about heaps, and they are very simple. So you can do it by the 9th of this month. They are very simple. Just implement a heap and a priority queue operation. Any questions? Okay. What is your question? Sorry? It's a generalization of a queue. If the priority is assigned according to their arrival, it's a queue. Okay? It's a generalization. And if you have any questions, very difficult to speak in English, I'll get a lot of questions after this class, then you can freely use your only Korean and English. I can't speak Spanish, Japanese, Chinese, no. Okay, then let's wrap up this class now and see you on Friday. Bye.